Now we're ready to talk about intervals for linear regression. There's going to be three different kinds. The first kind is going to be confidence intervals for the coefficients. So just as in the simpler case, we talked about confidence intervals for mu. Well, mu was the parameter of interest. Now, if the parameters of interest are beta naught and beta 1, we can come up with confidence intervals for those. Right, so these coefficients we're talking about are beta naught and beta 1 if we just have a simple linear regression, which means just one predictor. So the way we come up with these confidence intervals is exactly parallel to the way we've come up with confidence intervals previously. You take your estimate and you add or subtract 2 times the standard error of that estimate. And so we can say that the probability that this interval covers the true value is 95%. And I can write something similar for the slope. The probability that an interval equal to the slope estimate plus or minus 2 times the standard error of the slope estimate, the probability that that interval covers the true value is equal to 95%. So this is the same idea of a confidence interval that we've had all along. If you sample one time from the population, gather a data set, estimate, so the data set has an x and a y in it now, estimate the intercept and slope of a regression line, write down the intercept and slope, and now do it again, right? Sample data from the population, estimate an intercept and slope, record those intercepts and slope. If you do that repeatedly, right, and each time generate a confidence interval, as I've written out here, 95% of those confidence intervals will successfully cover the true intercept or the true slope. Again, if you repeatedly draw data and estimate one of these parameters, you will, and for each data set you draw, you calculate a confidence interval. 95% of the samples you could draw will lead to confidence intervals that are successful in that they cover the true value. Just to remind you, you've already seen previously when we talked about hypothesis tests, what these standard errors are at the square root of the variances. So we've got, well, the variance, the estimated variance of beta hat is sigma hat squared times 1 over n plus x bar squared divided by the sum of xi minus x bar quantity squared. Take the square root of that. And the standard error beta hat 1 equal to the square root of sigma hat squared divided by the sum of xi minus x bar quantity squared. And if you've not already seen that, then now you have. And just so you can imagine this in a regression output, you might have, like it says, intercept, and then you have your variable name, right? And then you've got your estimates of the coefficients. And so what it does is it lists the beta naught here and the beta 1 hat there. And then the next column lists the standard error. So here's the standard error. This is again what the R output looks like. And so if you wanted a t statistic, right? So the t statistic, for example, for the slope is just equal, assuming the null hypothesis is that the slope is 0. You take the estimate from the first column and divide by the standard error from the second column. What we're saying now is if you want a 95% interval, you take the estimate from the first column and add or subtract 2 times the standard error from the second column. And you can check at least this one because the third column is just t, so it'll exactly list that value there. But the confidence interval is not automatically shown when you do a summary of regression output. However, if the output, let me kind of put this over here so you have it. If the, this is in R, if the output is, if out is what you call your regression output, so you did y tilde x, then if you type conf int parentheses out, the confidence intervals for all your betas will come right out. So this is one type of interval you can make for regression, a confidence interval for your coefficients. And if your coefficients are quantities of interest, then that's exactly the right thing to do, right? That may very well be exactly the right thing to do. However, that's not the only kind of interval that you might be interested in. That's not the only quantity of interest that you might have in a regression. So the next idea is going to be also confidence intervals. Confidence intervals for the mean of y given that x is equal to some particular value that we'll call x naught. Okay, so let's think about that for a second. In our simpler example, when we weren't talking about regression, we said, hey, we're trying to come up with a confidence interval for mu. And mu was the parameter. But in that case, mu was also the mean of y, right? But in this context, our parameters are beta 0 and beta 1, and we just talked about coming up with intervals for them. But those parameters are not the mean, right? Beta 1 and beta naught are not the mean of anything, right? So actually, although in the simpler case, mu was both the parameter of interest and the mean of the y values, here it's two different ideas to come up with a confidence interval for the parameters or a confidence interval for the means. Let's use a picture to make sure we understand what we're trying to do here. So suppose that this is x and this is y, and this is my regression line, so it has intercept beta naught and slope 1. The idea is that if there's some value, x naught could be any number, we already know how to come up with the point on the line, right? Like, what is the mean of y when x is equal to 3, right? We know to just plug in x equals 3 into our regression equation, or estimated regression equation. But now, if this is the quantity of interest, I might want to say, well, what is a 95% confidence interval for the mean of y when x is equal to x naught? Because note that if I had drawn a different sample from the population, this estimated slope and intercept of my line would have been a little bit different, right? So my estimated mean of y when x is equal to 3 would have been a little bit different. So now what we want to do is write down a confidence interval such that if I repeatedly sample from the population, and for every sample, estimate a regression line, and come up with a confidence interval for the mean of y when x is equal to 3, and I do that lots and lots of times for different samples, I want 95% of those confidence intervals generated from different samples to successfully cover the true mean of y when x is equal to 3. So how do I do that? Well, let's see. I already know that the mean of y when x is equal to 3, or any number, x naught, I'm just using 3 as an example of x naught, again, is estimated by just plugging in intercept estimate plus slope estimate times whatever this number is. So that thing is going to be at the center of my interval. Okay, that thing's going to be at the center. So I'm going to have beta naught hat plus beta 1 hat times x naught plus or minus something. Okay, plus or minus something. Now it's possible to show that the central limit theorem holds here, and that if you repeatedly draw data sets and each time calculate this quantity, then a histogram of those quantities over lots of different samples would look normal. So because you know they look normal, we get to put a 2 here, okay? Plus or minus 2 times something. What is the something? Well, it's the standard error of this quantity that I've underlined in red. So I'm not going to derive it for you here, but instead I'm going to write it down for you. It turns out to be sigma squared times 1 over n plus, it's a plus sign, x naught minus x bar squared divided by the sum of the squared differences on x. So I can say that the probability that this entire interval covers the true mean of y given x equals x naught, in other words, covers the true value of beta 0 plus beta 1 x naught, that probability is equal to 95%. The probability that this interval that I've written down in blue covers the true value of the mean of y when x is equal to 3 is 95%. So that's how you do it. Now I want to actually look at this and try to understand the different parts of it. So what are the components? Let me write it down bigger so we can see it. So we've got a square root of this whole thing, sigma squared times 1 over n plus x naught minus x bar squared over sum of the xi's minus x bar squared. Okay, I'm going to parenthesis here as well. So this thing is the residual variance. And that had better be there, right? Because if the actual data points look like this, then I'm much more sure about where the mean of y is when x is equal to 3 than I am if the actual data points look like this. So the residual variance matters. Okay. What else matters? Well, this is an interesting quantity. This is an important one. The difference between the x naught that I'm interested in and the mean of all the x's in the data set. When this difference is small, right, then that contributes less to the width of this interval. But if this difference is big, if x naught is very far from x bar, then I've got this big positive squared term in this numerator that determines the width of the interval. So the intuition here, I'll just call this square distance from x naught to x bar, okay? If x naught is close to x bar, in other words, if the value for which you're trying to make a prediction is very, very close to the mean of all the x's, you're going to be able to do a good job because you have lots of data there. But if and you're going to have a pretty narrow confidence interval for the mean of y given x. But if the value for which you'd like to make a prediction is really far away, like maybe it's like x naught's way out here, right? There's a lot less data up here, right? And so I'm not going to be able to have as much confidence about where the mean of y is given x. And that gets translated into this confidence interval because this quantity I've circled in red becomes very big, which makes the width of the interval big. Then the other piece to look at is this thing and this thing. Now, both of these reflect the sample size, right? Note that they're both in the denominator. So if the sample size is very, very large, right? If the sample sizes are large, then both of the quantities in these denominators are very large, which in general makes the width of this interval, the confidence interval, less, right? Which should be intuitive. The more data you have, the more sure you are about where the mean of y is when x is equal to 3. So if the sample size of your data set is very big, then these two denominator quantities I've circled are big, which means the width of the interval will be smaller, right? Whereas if these two quantities are smaller, right, then you might still have a pretty wide interval. Again, there's not a lot of data, so I really am not so sure what the mean of y is when x is equal to 3. There's one other element here, one more thing to point out for this circled quantity, right? So this is the numerator of the variance. So I'll say it reflects the variance of x. How spread apart are the x's? If the x's are very spread apart from each other, and generally the x's are generally far from x bar, then this quantity will be big, which makes the overall width of your interval small. Why does that happen? Because if the x's are very spread apart, I do a better job figuring out what the slope of the line should be. And so if I'm pretty sure what the slope of the line should be and the intercept of the line as well, then I'll do a good job, finding this point here on the line. So let's look at a couple examples of that. So here's a case where the x values don't have a big range, and here's a case where the x values do have a big range, okay? It might be actually true that the slope is the same in both those cases. These might be two samples from the same true line. But here, I have a pretty good sense of that slope. Here, like I can draw it this way or this way. There's a few different ways to draw that, so it looks like it goes through those data points. Because I don't have as wide of a range of the x's, I'm just less sure of where that line should fall. So when the sum of squared differences in x are big, then you're able to make a narrower confidence interval for the mean of y given x.